Hello, everybody. We are going to start. Just before to let the floor to Florian Olorgen from the MIT, I would like to give the floor to Mathilde Gonon, who is the head of research and education at ENAC, for a few words before to go deeper in the webinar. Mathilde, if you want to take the floor.
Thank you. Thank you very much, Nicolas. So hello to all of you who are passionate about aviation and to all of you who wish to write a new chapter in its fascinating history. It is with a great pleasure and also a great satisfaction that ENAC and ISAE-SUPAERO are pleased to present our new Advanced Master in Sustainable Aviation, developed jointly by pooling all our energy, our complementary strengths, our excellence, and above all, our knowledge of aeronautics and air transport. We all know that the era of sustainable aviation has arrived. The time for speeches, demonstrations, and arguments are behind us. The time for action is here, with the entire aviation sector committed to achieving carbon neutrality by 2050. One thing we know for certain is that this is a global challenge. Every sector and every player in the aviation industry is affected and has already come on board. Yes, we must approach this challenge from a systemic perspective, just as we did with the challenge of safety. It was with this certainty that our two schools, 3 years ago, embarked on this adventure and this challenge to create an entirely new training program, innovative in its content and teaching methods, with a simple objective: to train and develop the skills of all stakeholders to devise concrete technical and operational solutions. Whether you are an aircraft manufacturer, an equipment supplier, an airline, an airport, a regulatory authority, you all need to devise solutions that will optimize air transport in terms of its environmental footprint whilst maintaining a high level of safety. Is this difficult? Is this impossible? Has this never been done before? A bit of history, please. When Charles Lindbergh prepared for his attempt to cross the North Atlantic in 1927, he did everything he could to optimize his aircraft weight so he could carry as much fuel as possible. So he removed the navigation instruments, his seat, the radio, the windscreen, and even the co-pilot. All pilots know that the great circle arc is the shortest distance between 2 points on a sphere. But is this the best route? It depends on the circumstances, the constraints, and the criteria you wish to optimize. In mathematical terms, we refer to this as the objective function. Thus, every engineer within this air transport system must and will need to know how to determine their own objective function, to set the specific trajectory for their equipment, their service, and their operations, deciding what to remove, what to add, to ensure that the systemic trajectory of aviation is optimal in terms of its impact on the climate. As centers of excellence that are deeply committed to and collaborate with all stakeholders, we invite you to join this training program, which is designed solely to enable you to take action. Through this accredited course, you and your teams will learn to, first, assess the environmental impact of a product or service in the aviation sector. Second, design new solutions for the sustainable development of the aviation sector. Analyze and improve complex situations in the aviation sector requiring a systemic approach, and support the implementation of disruptive solutions. Here are a few examples to illustrate in practical terms what you will be able to achieve upon completion of this course. First example, as a final assembly line engineer, for instance, you will be able to optimize the various stages of the production process, acting as an architect of the green transition. Second example, as a propulsion and engine engineer, you will be able to manage the integration of sustainable aviation fuel by addressing the resulting safety issues as well as certification requirements to design future propulsion systems. And third example, as an engineer at a subcontractor manufacturing electrical components, you will know how to implement their eco-engineering process. So thank you for your attention, your interest and your commitment. Please do not hesitate to join us on the Advanced Master in Sustainable Aviation. We hope to see many of you there as the engineering challenge ahead us requires all to work together and pool our expertise. Thank you for your attention.
Thank you very much, Matti, for this very nice introduction and give the context of this webinar. So I'm pleased now to welcome Florian Alrogen from MIT, who is a professor in economics at MIT. Florian, can you hear us? Can you turn
loud and clear?
Okay.
Yeah, good afternoon or good morning for me, everyone. Let me share my screen.
Yeah, the floor is yours, Florian.
Excellent. Perfect. Yeah, good morning on my side. Good afternoon to you, everyone. It's a pleasure to be here. Thanks for the kind introduction, for the invitation to be here. My name is Florian Alrogen. I'm principal research scientist at MIT and the executive director of the Lab for Aviation and the Environment. And what I would like to do over the next 30 minutes or so is to dive deeper into this question of sustainable air transportation, specifically on the climate question for air transportation. Going basically through two steps. First, talking about what actually causes the climate impacts of aviation, and then actually develop a strategic perspective together on how to think about the mitigation of these challenges, really sort of ending on a point where we can talk about like, okay, what would it look like to create a near zero climate impact aviation sector? So my presentation is going to be structured accordingly. We'll start really with this question of, okay, what are the mechanisms behind the climate impacts of aviation? And then we will dive deeper into the technical feasible and economically viable pathways to mitigate these impacts, which will be very much informed by our understanding of what the pathways between the climate impacts, what they really are. So without further ado, let's jump right into it. And let's start by actually thinking about the mechanisms behind the climate impacts of the aviation sector. In order to do that, we need to start at the beginning. We need to start with an aircraft flying from A to B and what it actually leaves behind, its emissions. And for as long as we're using fossil jet fuel as our aviation energy carrier, chemistry basically dictates what these emissions are. It's by mass, 71% CO2, it's 28% water vapor, and by mass, less than 1%, it's a range of different pollutants, such as nitrogen oxides, sulfur oxides, unburned hydrocarbons, black carbon, organic carbon, all these kinds of things. The point, though, is that we're not particularly interested in the emission themselves. What we're actually interested in is what the impacts are that are associated with these emissions. And as already noted, I'm going to focus today on the climate impacts of aviation. Most importantly, when we talk about climate, we need to talk about the CO2 impacts of aviation. They result from aviation being more than 99% dependent on fossil fuel today, which means that we're taking fossil carbon out of the ground, we refine it into a fuel, we combust the fuel, release CO2 into the atmosphere, thereby increasing atmospheric CO2 concentration. And given that CO2 is a greenhouse gas, this leads to the warming impacts that you're all very familiar with. This is an important driver of the climate impacts of aviation, no question. However, aviation is a little unique in that the impacts of aviation do not stop here. There are additional climate impacts that actually come to bear. The first mechanism that we need to talk about are contrails, condensation trails, the white line-shaped clouds that you sometimes see forming behind aircraft. These form through a actually relatively simple mechanism. as I'm showing you here, 28% of the emissions from an aircraft engine by mass are actually water vapor. They're emitted at high temperatures from the combustion process of the engine, but into ambient conditions which are actually very cold at altitude. So what happens as the emission happens is that the exhaust stream of the aircraft starts to cool. And what happens with warm water as it actually gets emitted into a cold atmosphere and actually cools? Well, what it actually happens, it condenses. The water condenses, particularly on particles that are already in the exhaust plume of the airplane, especially soot, and form water droplets. And you know that mechanisms. If you breathe out on a cold winter morning, you make this little cloud. Well, that's kind of the same thing that actually happens here. So you make little water droplets first. Now, if it's sufficiently cold and sufficiently humid, what actually happens is that these water droplets don't evaporate, but they actually freeze and they form ice crystals. And these ice crystals can continue to grow, and that's exactly what you see. That is the contrail. It's nothing else than an ice cloud, like a natural cirrus cloud. However, if you actually look at contrails, and oftentimes when you look up into the sky, you don't see a contrail at all because it isn't cold and humid enough. Sometimes you look up into the sky and you see a situation like what you see in this little picture here, where something formed, but it basically doesn't persist. It evaporates right away. This may not even be ice. This may actually just be liquid phase. In any case, we have these non-persistent contrails which last seconds to minutes. These are the contrails that we do not worry about. They simply don't last long enough to actually have a meaningful impact. What we worry about is if the contrail actually persists first in its linear shape for minutes to hours, and eventually over hours it may become diffused and persist over long periods of time. But it's this persistence that's actually important for the impacts of the contrail itself. Why? Well, for that we need to understand the mechanism, how a contrail actually affects the climate. If you think about a contrail, just like any other natural cirrus cloud, it actually has two impacts. Number one, it reflects incoming sunlight back out into space. And you know that that is a cooling effect if you've ever been sitting in the shadow of a cloud while you're trying to sunbathe. It is cooling. However, at the same time, what a contrail does, it's like a layer around the atmosphere, right? And it traps outgoing heat that's trying to escape our atmosphere. And this trapping effect is a warming effect, which you're also very familiar with, because if you have to compare a cloudy winter morning to a clear winter morning, you know that the clear winter morning tends to be colder because of the very same insulating effect of the cloud. The problem with now any contrail is that whether it is warming or cooling now depends on the balance between the warming and the cooling effect. And the result is entirely situational. If you think, for example, of a contrail at night, then you do not have this reflective effect. You only have the warming impact. So a nighttime contrail is almost certainly warming, while a daytime contrail may be warming or may be cooling. The point here is that while this situation is situational, the warming effect for the average contrail, that's what the science agrees right now, is warming. So we can take note of that. Then we need to take note of additional non-CO2 climate impacts of aviation, from the water vapor emissions, which tend to be warming. Nitrogen oxides leads to a bunch of atmospheric processes, some leading to cooling, some to warming effects. So it's a little more complicated. Sulfur oxides tend to be cooling. Black carbon tends to be warming. The point is, this is a relatively complex picture where you see some cooling, some warming effect. Warming tends to dominate. That's our current scientific understanding, but clearly it's a more complex picture. And it's not only complex because of this, it's also complex because the time scales at which these impacts happen actually vary quite substantially. Take CO2. If you have CO2 from a flight today, it stays in the atmosphere for hundreds of years. And while it's not particularly dramatically warming at each time step, the warming effect integrated over this long period of time is the problem of the CO2. Compare this to a contrail. A contrail lasts for a couple of hours. It's a very short-lived impact through which it actually exhibits the warming. And these time differences, they're very important to understand because they actually matter a lot in how much we think these impacts matter. Now, these emissions don't only have climate impacts, they also have impacts on air quality through emission of or formation of air pollutants such as ozone or fine particulate matter, which we breathe in at the surface, which actually has health impacts. This comes from both cruise and LTO emissions. These are important impacts. I'm not going to focus on them today, but that doesn't mean that they are not important. They're actually quite important, but I would like to stay focused for today on the climate impacts here. Now, you may ask, how big are the climate impacts of aviation? And in order to answer this question, you may have seen different metrics being proposed to actually analyze this. Things like radiative forcing, so energy balance in the atmosphere, things like global warming potential that actually integrates radiative forcing relative to CO2 over longer periods of time, like 10 years, 20 years, 50 years, or 100 years. Global temperature potential, which actually looks at temperature change that could actually result. All of these are physical metrics that actually give you a sense of what is it that we physically change in the energy balance of the planet, etc. So it's a very much a way to tie this to things like temperature change. The problem is that these kinds of metrics for decision making are often not very understandable. They're not very understandable because they don't mean much, and you need to make trade-offs with sort of like investment costs or things like that. And you can't do that based on these metrics, which is why a lot of people use what I would call monetary metrics. Metrics that try to quantify the monetized impact of an emission on the socioeconomic system through warming, considering all the future impacts of the emission. So what does this mean for a modeling chain? Well, you model the emission of an aircraft. You then model what this means for the atmospheric concentration and energy balance of our atmosphere. Then you model what this means for temperature change. And then you translate this temperature change into socioeconomic impacts. This is where the social cost of carbon literature comes in. This is what William Nordhaus actually got a Nobel Prize for in economics, to really say, okay, what is the socioeconomic damage that is associated with temperature increases? This can be things like yield changes. This can be things like, crime, things like health, things like that can actually drive these socioeconomic impacts. Now, if you do this monetary analysis, which we do on a regular basis, you can look at the aviation impacts of all the aviation emissions in dollars per ton of fuel burned. And you really look at this sort of like this external cost to society. This does not include the cost of the fuel itself, but just the emissions. And here's our latest assessment of what this looks like. You see, we start with some negative costs because some of these emissions actually lead to cooling effects. And then you look at the warming side and you see there's a bunch of smaller impacts, but basically the warming side is pretty much 70% driven by CO2, 30% driven by contrails. That's sort of like the key results that we derive there. And the total externality is about $500 per ton of fuel burned. If you compare this to the current very high price of jet fuel of about 1,500 tons, it's about a third of that, which gives you a sense that this is pretty substantial. And even more so if you look at the historical cost of jet fuel, which are on the order of $600, $800 per ton of jet fuel, then you see that this is a pretty substantial externality that we are talking about. Now, is this my final number? No, because there's a lot of variability in how you can actually assess these impacts. Most importantly, this comes from the question of lifetime. Again, remember, CO2, once emitted in the atmosphere, stays there for hundreds of years and is warming for hundreds of years, a contrail, a very short-lived effect. And variability arises simply from the question of how do you actually trade off an impact today in the contrail versus very long-lived CO2 impacts, hundreds of years in the future. How do you make that trade-off? And that's a societal question that societies may answer differently at any given point in time between different societies. And this may simply change, and it can really drive substantial differences in these impacts evaluations. Don't want to go into detail, but this little graphic here on the bottom actually shows you how dramatic these differences can be. But it's not only variability that matters. It's also uncertainty that matters, because especially in the contrail impacts, there's a lot of things that we do not fully understand about contrails, like ice crystal properties, lifetimes, things like that, that can really still drive this impact up or down, right? So we need to acknowledge that from a scientific perspective as well. All of this leads me right into my second point, the question on, okay, now that we understand where this climate impact is coming from, What can we actually do to mitigate it? In order to do this, people love to make like long laundry lists of actions that you can take. However, I don't like laundry lists. I want to give this a little bit of structure. And in order to do that, what I would like to do is I would like to start with a very simple model of what actually drives the total climate impact of aviation. And it's basically the product of three things. It's the level of activity, the amount of flying, the passengers kilometers or the ton kilometers that we have in the sector, times the energy intensity of the flying activity, basically the fuel burn per passenger or ton kilometer, or for the US audience, the inverse of US fuel economy, and times the impact intensity per unit energy that we are using. Well, this is basically exactly the metric that I just showed you, dollars per ton of fuel burn. That's impact intensity. So the nice thing about this framework is that we can now take different measures to really reduce the climate impacts of aviation and track it to these three buckets. We can talk, for example, about activity-based measures, things like mode substitution, going to other modes of transportation like rail, which we really see ongoing in Europe, as a way to reduce aviation's climate impact. We know that the amount of impact that we can get out of this is relatively small because aviation is an intercontinental mode of transport. We really do not have a mode to substitute with. The alternative to reduce activity is to suppress traffic, basically tell people that they shouldn't fly. That is, in my mind, very limited too, because we need to acknowledge that we are not joyriders when we get on an airplane, but we fly because we want to get to a destination, and we derive a benefit out of that. If we can't fly, this benefit is lost, and this is can be a pretty substantial cost to society that don't make it necessarily a good choice to do traffic suppression as well. But that's a question of analysis, obviously. So activity-based measures. Also, in reality, we need to acknowledge that the aviation sector globally is continuing to grow by about 4% per year, especially in emerging economies. So if anything, activity-based measures, they won't really reduce. And if anything, we will see increases in activity over the coming decades. So if that is not solving the issue, then we need to talk about energy intensity measures. Energy intensity measures can be basically two things. Number one, aircraft technology improvements, which can be the airframe, which can be weight reduction, drag reduction, or the engine, which is just more fuel efficiency out of the engine. And if we historically look at how much we have improved our aircraft, we can see that a new aircraft in 2025 compared to 1970 is about 45% more energy efficient per ton kilometer or passenger kilometer that we actually offer. So there's substantial progress there. On top of this, we need to acknowledge that better operations can also make a difference. We just recently did a study here at MIT to actually look at the global fuel inefficiency of cruise flight, and that's on the order of about 8%. 8% of fuel burn that we waste basically because we do not fly optimal routes, wind optimal routes, etc. So the problem with that is we can't, get to all the 8% because some of this is due to conflict. We can't fly over the Ukraine or through Russian airspace. Some of this is driving this, but some of it is true inefficiency where we could simply get better in how we fly our aircraft. And having these efficiency improvements is important for the sector. It's economically very important for the sector. If you look at it at a very high level, sector in 2025 was about $1 trillion of revenue, expenses on the order of 940 billion. Out of which about 27% was fuel. If you compare the two, that means we had an operating profit of about 66 billion. So that's about 6.6% operating margin. That's really small for an industry. Now, what if you magically could get access to a 2025 aircraft? 1.5% efficiency improvement per year over 25 years, 5% more efficient operations, a 35% reduction in fuel burn. That would be a saving of about $88 billion. You could just, in the same operating framework, you could basically increase the profitability by 2.5. It's not a forecast. This is not how it would happen, but it gives you a sense how important efficiency is. Now, The last thing that we need to acknowledge when we talk about energy intensity, as important as it is, and as important as it is not only for sustainability, but also for the economics of the sector, we need to acknowledge that we are unable to reach zeros through energy intensity measures, because bringing mass from A to B fundamentally requires energy. It's kind of the definition of energy, so we won't get it to zero. And in fact, if you compare it to the activity-based increases, energy intensity really tends to be outgrown by market growth historically. And we have no reason to believe that this will change in the near future. So if activity doesn't solve it, if energy intensity doesn't solve it, then it needs to be impact intensity that solves the issue. And if you look at impact intensity, well, we looked at this in the first part of the presentation. What is warming driven by? Well, CO2 and contrails. These are the two things we need to solve. We need to solve the CO2 challenge for aviation, which requires low carbon energy transition for the sector, and we need to solve the contrail challenge for the sector. So we need to dive into these two buckets in a little bit more detail. Let's start with the fuels and the low carbon energy transition. As I mentioned earlier, the problem results from us being right now 99.4% dependent on fossil fuel, meaning we take carbon from the geosphere, we refine it into a fuel, we combust the fuel, we release CO2 into the atmosphere, increasing atmospheric CO2 concentration. That's the key issue that we need to escape from. How do we do this? Well, first step that we can take is drop-in fuels, sustainable or synthetic aviation fuels, or short SAF. Fuels that are chemically very similar, if not identical, to fossil jet fuel, so that we can use them with existing aircraft, with existing infrastructure, and with the aircraft that we're going to build over the next decade or so, for sure. Now, you may ask the question, if they are chemically very similar, they are hydrocarbons, you burn them, you release CO2 into the atmosphere, where's the advantage? Well, the advantage comes from the fact that we make them from things like biomass, right? Where we now use this carbon from the biosphere to make the fuel, combust the fuel, but this carbon ended up in the biosphere during the growth of the biomass through photosynthesis. So we have a perfect carbon cycle, which at least theoretically makes this fuel carbon neutral. It doesn't have to be a biofuel. It can also be a power-to-liquid fuel, where you now capture the carbon from the atmosphere synthetically using processes like direct air capture, combine it with hydrogen, convert it to a sustainable aviation fuel, and release the CO2 back into the atmosphere through combustion. Same idea. This is why these SAFs have received lots of attention. We can use them with existing aircraft, and they could be theoretically carbon neutral. So a lot is currently going on in policy land, but also in terms of commercial activities to scale them up. However, we need to acknowledge that these fuels are not perfect. There are three key challenges that I quickly want to talk about. Number one, these fuels do not, despite the closed carbon cycle argument, do not usually mean that we have a full carbon abatement for the sector. And that is because of emissions that arise in the life cycle of the fuel, of making it, right? The agriculture that you need to do, right? The tractor you bring on the field, the fertilizers that you use, they usually cause emissions. Converting biomass into a fuel is a complex process, lots of pressure, lots of temperature, typically made with fossil fuel. Well, there are more emissions. And then and only then, when you combust the fuel, that's where you have the closed carbon cycle. So if you look at the full life cycle of the fuel and compare per unit energy the emissions of a fossil jet fuel, including all the pumping and refining, etc., to many SAFs, you may not see a carbon reduction at all, despite the closed carbon cycle argument. For others, you see this 80–90% reduction in carbon intensity. That's problem number one. Problem number two, these fuels are really expensive. If you actually look at the 2025 situation, we had about an $80 to $100 per barrel price premium, or a factor of 2 basically, for sustainable aviation fuels, even after incentives on the US West Coast. So these fuels are really expensive. Now you may say, well, wait a minute, with the current high jet fuel prices, have we solved the problem? Well, this is where the current jet fuel price is in the current crisis on average. That's pretty much where the SAF price is. So problem solved? No, problem not solved, because the SAF price has also gone up. In fact, the SAF cost premium has actually jumped up, which is a good thing, because people realize that SAF is a good substitute. We, in the short term, had inelastic supply, so people wanted the SAF anyway. The SAF price jumped up, creating a price signal to actually create more capacity. But you see, this is an interesting market dynamic there. But if you look at it in the long term, SAF is going to be more expensive, even if we learn how to make it cheaper, even if we scale it up. It's going to be more expensive than conventional jet fuel at the price levels we had last year. It's somewhere going to be in the range of where the current jet fuel price is. This is something we need to get used to, and we need to somehow be able to cover. That's the second challenge. The third challenge that I want to talk about is a fundamental. It's a fundamental question of, can we scale SAF up to scale? And if you ask this question, well, there's a question of how much feedstock do we have available? And if you look at bio-based SAF, well, it's a question of the bioenergy. IPCC in its last report told us we have about 5 to 50 exajoules of primary bioenergy potential from waste and residues, and about 50 to 250 exajoules per year from energy cropping sustainably. Now, is this enough? Well, to judge this, we need to compare this to the energy demand of tough to decarbonize transportation, which according to the IEA by 2050 would be about 77 exajoules per year. Now you compare these two numbers and you say, well, waste and residues almost certainly won't be enough. With some energy cropping, it seems to be okay. I warn you, that's not quite right, because the left side here is actually primary bioenergy, what's in the crop. The right side is fuel energy. Getting from primary to fuel usually has a conversion efficiency of about 50% or less. So the 77 exajoules of fuel in primary is more like 150 exajoules. And you see how challenging this will be with biomass, even with energy cropping. Now, you can say, okay, that means we need to go to power to liquid fuels. The amount of electricity that we will need for that to cover all of aviation by 2050 with power to liquid fuels on the order of 15 to 18,000 terawatt hours. That's about 50 to 80% more than all the renewable electricity we're making in the world today. We can make this electricity if we want to, but what we will need is substantial investment, between $9 and $18 trillion that we'd have to invest just for the energy for the aviation sector, which is a lot of money for a sector that currently spends about $250 billion a year for its entire energy supply. At this point, you may ask, is it better to just not do sustainable aviation fuels because it's complicated to make these long-chain hydrocarbons? Is it better to go to hydrogen, to go to electric aircraft? The intuition is clear. It's much easier to make the energy. However, it now depends on the aircraft whether we can do it. We know electric airliner-sized aircraft are not feasible today in any form. Okay, but that's a topic for another time. Let's talk about contrails for a moment, because contrails also need to be addressed. And people have talked about different ways on how to really address the contrail things. Engine or fuel modifications that could reduce particle emissions that lead to less contrail formation. That's something you can do, but it will take a long time to implement. And there are lots of scientific questions that are still unclear, which is why people are excited about flight path deviations, simply flying through the regions where contrails form and persist, which are regions where it's sufficiently cold and sufficiently humid. And that's not everywhere. Those are horizontally large but vertically thin regions that you can fly around with simple flight altitude adjustments. However, this leads to a trade-off, because if you adjust your flight altitude, you do actually leave the fuel optimal altitude, which means that you will increase your fuel burn. This trade-off needs to be understood. However, there's good literature to understand it with. The current studies implicate that for probably far less than 1% of additional fuel burn, you can avoid more than 90% of contrails. If you say that about 70% of warming comes from CO2 and 30% comes from contrail, that means that the 1% fuel burn increase is a 0.7% climate cost, while the 30% reduction of the 90% reduction of 30% is a 27% reduction. So you see, this is highly beneficial potentially to really do these avoidance maneuvers. Now it comes at a cost of about $2.5 billion in additional fuel burn for the global airline industry, which is about 6.4% of profits, 0.3% of revenue at about $1.20 per ticket, to avoid about 30% of aviation's warming impact. This is very, very promising. However, there are lots of questions that still need to be answered to figure out whether we can actually implement this at scale or not. But the promise is there, which is why a lot of work is going on in this area. I want to close with 3 takeaways for you. Number 1, I hope what you take away from this is that if you talk about climate impacts of aviation, this is not just CO2. This is CO2 and non-CO2. But non-CO2 unfolds on different timescales. So asking the question on how we actually trade these things off is a little bit more complex, number one. Number two, I hope what you take away from this is that with growing global mobility, we need to increase energy efficiency and we need to decrease impact intensity as crucial paths to net zero aviation. Now, this is really important because this means we need an energy transition and we need to work on contrails as well. And lastly, the economics of the transition. I gave you some glimpses into this, but I hope you take away from this that these economics of the transition, they are really challenging. And a business model, a robust business model to incentivize investments necessary to really get to near zero, that is something that we still need to figure out. I'm going to leave it there. Thank you very much for your attention and happy to take some questions.
Thank you very much, Florian, for this very good talk and presentation of the challenges. We have a bit of time now for a few questions. So if you want to ask one of them, don't hesitate to use the chat. Maybe there is just a first question about you mentioned the key role, Florian, of SAF. But you need biomass for that, probably. And do you have some idea of how you can allocate this biomass, this bioenergy to aviation or to road transport, for example? Because you mentioned also this sector. So do you have some intersectoral evaluation of the most efficient way, optimal way to allocate these resources?
Yeah, that's a fantastic question, and it's a question of what your alternatives are in different modes of transportation or even different industries, right? So in my view, I think for road transport, with maybe the exception of very long distance trucking, I think electrification is the path to go, right? So I think we can take road out of this. At least then if we talk about long haul trucking, there is a chance that we need to do it. Maritime shipping and aviation will actually have to fight for some of this biomass, but it's not just them, right? It's also other sectors of the economy, including things like bioenergy and carbon capture and storage that actually will be very much competing for this biomass. I think an important question that you're raising here is the question of like, okay, so should we take this biomass to other sectors first? The reality is that making these long chain hydrocarbons fuels for sustainable aviation fuels is not a very efficient way to use this biomass. However, the question is, do you actually have other alternatives available that you can more readily apply in other sectors so that this biomass can be left for the aviation sector or to maritime shipping to a degree? I think that's sort of like the market mediating effect that then has to come into play, whether a sector like aviation is able to pay a premium for this biomass that actually helps other sectors apply other, for example, electrification measures. I think that's sort of like how this will play out in the long term. I am aware that this is not the most efficient way to use the biomass, but that may not be the most relevant question. It's all about the relative advantage, not the absolute advantage.
Thank you very much. We have another question about you mentioned near zero target rather than net zero. Can you comment on the difference between these two notions, please?
Yes, absolutely. So I very intentionally here used the near zero target for two reasons. Net zero implies that you can take out of sector measures to really reduce impact, right? Do things like offsetting, do carbon removals, etc., which I think needs to be part of the final solution eventually. However, I think it is very important for the aviation sector to only think about carbon removals and out of sector activities to the degree that it's really necessary, right? I think it's very important to think about what can we do in the sector itself before we think about what are the residual emissions that we will need to deal with through carbon removals. So this is why I'm not actually using the term net zero here, but the term near zero here, knowing very well that not all the emissions in the aviation sector are probably can probably be mitigated entirely in the sector. So there will be a chance, there will be a role of carbon removals in this story eventually. And very, very, very good that somebody picked up on this very conscious word choice here. Thank you very much. I appreciate that.
Thank you very much. Maybe one last question before you move to the next presentation. According to you as an economist, what could be the next step to make aviation near zero carbon?
This is a wonderful question. And in my mind, I think we need to be very realistic about the timelines and what's going to happen. I think it's pretty clear that the two things in the shorter to medium term that need to happen is very clearly the scale up of SAF, where I think it is very important that we see the scale up of capacity and use over time, right? We were last year, we're at about 0.6% of the aviation energy supply that was met with sustainable aviation fuels. I think this is going to be a battle of the 1%, the 2%, the 3%, the 5%, the 10% over the coming years. And that's where we need to go. And I think this is not just a policy question. This is also a question of building a viable voluntary market that can really send a market signal into this whole ecosystem. That's one thing. I think the other thing that really needs to happen, and that's not so much short term, it's more medium term in my mind, is that we really figure out how to do control avoidance. There's so many unsolved scientific questions that still need to be solved in this context that we need to work on. This is still a scientific problem in my mind. But if we can solve it, then this is going to be another very quick path to really get to it. And then from there, we'll have to work out what is the long-term solution. Is it really going to be SAF? Is it going to be something else? I think that's the research that still has to be done and will have to continue to be ongoing while we actually scale up SAF at the same time.
Thank you very much, Florian. There are still some questions, but I'm sorry, we have to move forward for time reasons. So I suggest to send you the questions, Florian, and maybe we can answer by to write an answer to the participant after the webinar.
Absolutely, I'd be happy to do that. Thank you.
Thank you again, Florian. It was excellent. Now we can go with Marie-Pierre Cassagne, who is an expert in sustainability and transition. So are you ready to take the floor, Marie-Pierre?
Yeah, thank you very much. So first I will share my slide and I will start a very short presentation. Okay.
We can see the presentation. It's perfect. Thank you.
That's good. That's good. So hello, everyone. It's really great to connect with you. So in Florian's session, you explore the climate challenges aviation face today. And what I would like to do now, it's really to invite you to consider your own personal challenges. If you're here today, it's probably because you can relate at least a little to the situation of the person shown here. So what happens if the two planes diverge? This illustrates the tension between ecological concern and a job that may not fully align with those values, while still having to provide security and stability for the people who matter to you. So the question becomes, how do we move beyond this uncomfortable position? And to begin answering that, we are going to explore what solutions exist today and what concrete options are available for you. So let's explore your sphere of influence. In fact, we could distinguish 3 circles. The first one on the outside is the circle of concern. It's things that are important to me, but over which I have no power to change. I am concerned about inequality. I'm concerned on climate change and material resources depletion. I'm concerned about the world my children will live in. In the middle, we have a circle that things that I can influence directly or indirectly. And at the center are the things I control. So probably many of you, like me, have little decision-making power or control So it's important to think about how you can use your influence. And keeping in mind that taking a proactive approach can help you expand your circle of influence, as can leveraging your teams and network to amplify your impact. I would like to take a very personal example. A friend of mine arrived once at home with a game. It was a card game designed to teach people about climate change. He imagined it to help his students understand the consequences of climate change. So we decided the same evening to start playing it in a bar with 3 people. And in fact, the fact is that he has really a vision. He told me that he has the goal to reach 1 million participants playing this game. And the next week, he started to use it with his students. Then, during the semester, he convinced his engineering school to deploy it for all students. And discussing with colleagues of other universities, they decided to do the same in their universities. And myself, I also propose it in my company. So it was not so simple at the start to convince the engineering director to deploy it. But now, 5 years later, 75% of technology and engineering employees have done the climate fresk, and 2.3 million people have played all over the world. So we can really ask ourselves these 3 questions. What are my concerns? What can I influence? And on what do I have control? To identify where we can maximize our impact. Oops, sorry. I don't know why it doesn't work. Okay. Yeah, okay. So now I would like you also to ask 3 more questions. First of all, given what Florian explained about the drivers and the challenges the aviation sector transition, how can you identify what needs to be done to ensure a successful transition? What work is required? He talked about improving aircraft performance, but that's it, not really new. We can work on optimize the entire system, operating it better, but we can also deploy new energy infrastructure, SAF, hydrogen, and taking new success criteria into account also, and researching on unintended consequences. So there's a lot to dig into. Now you can ask yourself, what are you good at? What are your current skills? How can you make the air transport more sustainable using your current skills, or by acquiring new ones, perhaps doing the Master in Sustainable Aviation? Identify how you can make an impact. And finally, my last question is about joy. The feeling of making an impact brings satisfaction. What feels right to you? Be yourself. But perhaps also other facets of yourself are waiting to be revealed. The transition of our sector is really a good reason to explore them. So this Ikigai model is a way to reflect on how to align with your aspiration. How can you bring the 2 planes close together? So the good news is that there are plenty of opportunities in your current field. Check out a very interesting study conducted by Les Nouveaux Géants and who is available online. We tend to focus only on the design phase, but in fact, many other professions will be impacted. If I take, for example, purchasing department, which must start today by motivating their request for proposal to include sustainability criteria and also help their supplier grow and meet these new criteria. In finance, with the creation of new products to finance the company transition, such as green bonds, and of course, all aspects of non-financial reporting. In human resources, how can we offer training to help the company transition? How can we support employees? And of course, in manufacturing, how can we avoid energy waste and account for energy consumption right from the design phase of a production line. But a lot of other examples exist. Well, if we take a step back and look at the bigger picture, how can we envision the long-term future of air transport while taking planetary boundaries into account? We can see that it's a complex system, a system that will need better coordination among stakeholders. This will create a need for specific skills to bring airlines, airport, air traffic controller, and aircraft manufacturers together, but also institutions and civil society. We can imagine that we will need people with dedicated roles to facilitate dialogues among these stakeholders. So, what kind of competency framework could we imagine for such new roles? I found one framework that really resonates with me. It's coming from the Mines Telecom Institute. It's a compass with 4 directions. The first one is knowledge. We should systematically analyze the impact of human activities on ecosystems and the climate. The second one is technical skills, to create value chains that support a sustainable future. But we should also embody individual responsibility to act collectively by knowing ourselves. So interpersonal skills are key. And then we need to apply a historical and forward-looking approach that fosters critical thinking and decision-making, to know how to see the big picture through analytic insight. And that's pretty much what we are aiming to offer in the Sustainable Aviation Master Program. And I will give the floor to Nicolas in a moment, who has the chance to show you what it looks like in the next slot. As you can imagine, there's also plenty of options to get involved in the transition in other ways, through association, unions, and a lot of others. So you just have to find your own way. Thank you for listening.
Thank you, Marie-Pierre, for sharing your view on the difficulty to be in line with your work and personal values. Very excellent talk. I would like to take a few minutes now to give you a brief overview of the postmaster degree mentioned by Marie-Pierre. So yeah, maybe I can start with my name, Nicolas Gourdin. I'm a professor at ISAE-SUPAERO, head of education program in Sustainable Aviation here. And yeah, I would like just to give you this overview about a full online remote education program in aerospace and aviation that deal with sustainability. So here is a view of this program. The content is quite large. We are targeting 4 different skills. The first one is to be able to understand the problem. So for that, you need to be able to evaluate the environmental impact of on aviation, of an activity related to aviation. And then the second skill is that you need to propose some solutions adapted to overcome the problem. So then you should be able to translate these solutions into more complex systems and be able to imagine some prospective scenarios, a new world where these solutions could be effective. So the program here is a 1-year program that deals with different topics you can have on the screen here about aviation and environment. The energy, we talked about a lot with the intervention of Florian about the role of energy, typically SAF, but also H2 or electricity. And so I think it's a very important part of the future of aviation. Then you should be able to deal also with certification and environmental law. So it's not just a program about technical lovers. We focus a lot on technical lovers, but not only. I think it's important to have a much broader overview, including some economics and laws that apply to air transport that are quite specific. A core aspect of the program is about eco-design. How you imagine work and adapted design to be more environmental friendly products and including products and services. But let me just to show you some examples of this program. Let's start with air transport. We are not focusing only on the aircraft or just aviation. It's we are considering the full air transport system, socio-economic system. I think it's important to have this in mind because there are some interactions with geopolitics, with economy, with societal challenges also. So I think it's important to have this kind of map in mind if you want to be able to evaluate the levers that will make aviation more sustainable. We also consider some interviews with engineers like Airbus engineers. And this is an example of an interview with Olivier Canal, who is engineer specialized in raw material. The question is not what will be the future of aviation, but is it possible to build this future aviation with the available materials in the world? So this is the kind of topic of this program. It's part of this program. Then we can explore a full range of potential levers. The idea here is to evaluate on a scientific basis all that is available to make aviation more sustainable. So it includes, for example, in the very short term, the fleet renewal. For example, we have to improve the fleet efficiency. So what can be done to do that? You can need to activate some new levers like better aerodynamics, lighter materials, and so on. So you can still increase a bit the efficiency of aircraft, but the question is, in which extent is it still feasible? I will not detail all the levers, but we have also some courses about some non-CO2, most of non-CO2 effects that have been mentioned by Florian in his speech, for example. It's a very important part of sustainability, as it has been said. A large part of the climatic impact of aviation comes from these non-CO2 effects. So then, of course, we will deal with dropping energy, alternative energy carriers, but also non-dropping like H2 electricity. What is the potential of this technology? Which are the main limitations or challenges, current challenges that can be more or less difficult to overcome? We have some levers related to economics or to policy also. And at the end, what has been mentioned by Marie-Pierre about the role of individual behaviors, for example, including sufficiency. So as I said, I won't detail everything, but I'm also pleased to announce that we have some international academic professors like Stéphane Gosling that gave a talk about tourism and the drivers of emission growth, but also his view on how you can reduce the impact of aviation for tourism and the different levers you can activate in order to make it more sustainable. So at the end, this is the full one-year program, but we have also some derived projects like certificates or MOOC that are ongoing and that will be delivered by the end of the year. So I would like to stop the presentation of the program in itself, but the best is that you go evaluate some of these courses by yourself. So we propose two examples of very short courses you can find in this program. So you can use the code online here to access to two nuggets that will discuss the impact of aviation on climate change. It has been largely discussed also with Florian. And then another one on the basic concept on climate change, international legal regime. So we will share the presentation, so you will be able to access to these two resources. So I'm going to stop here and keep a bit of time for a Q&A session. So don't hesitate if you have some questions about this program or previous presentations, including the one of Marie-Pierre. Thank you. So there is a question about is the program fully online? Yes. About 85% of the program is asynchronous, so it means that you can follow all the activities by yourself. So it is tutored, but you don't need to be in your classroom at the same time as another participant. And then about 15% of the courses are synchronous. So it means in this case you will share time with others, but everything is online. So it's an international program adapted to this kind of audience. Okay, is there a specific intake date or anytime you can register? So you can apply right now. The idea is to open very quickly, but you can already register and apply for this master degree, this advanced master degree in sustainable aviation. So please send an email to info@tsae.fr, or just you can go online and learn more about the process. Okay, it's already a bit more than 2 p.m. So I suggest to stop here. If you have some questions, don't hesitate to contact us to the mail that is in the chat. And if you have still some questions, we can address them by email. Thanks again for joining us. Thanks for your questions and participate to this webinar, and see you. Thank you very much. And thanks to all the participants, especially special thanks to Florian Alrogan for his nice speech.